Welcome friends to my YouTube channel. Now, yesterday I have discussed about second order phase transition, and also I told about Ehrenfest equation for second order phase transition. Now in this video I shall going to discuss a new topic, that is the equilibrium condition between two phases, say liquid and vapor. Okay. In this lecture I shall going to discuss the equilibrium condition between two phases, say liquid and vapor. Okay. Now, in order to establish the equilibrium condition, we consider a unit mass of mixture. Okay. Say m1 is the mass of the initial phase, that is liquid, unit mass, and m2 is the unit mass vapor. Okay. So we consider a unit mass mixture. Okay. Unit mass mixture of liquid and its saturated vapor. Okay. So obviously from which we can write dm1 plus dm2, this is equals to 0, and that means we can write dm1 this equals to minus dm2. This gives a name, say 1. Okay. Unit mass of mixture, that is m1 is the unit mass liquid and m2 represents the unit mass of vapor. Okay, so from which we arrive dm1 equals to minus dm2. Okay. Now, if g1 and g2 represents the specific values of Gibbs potential corresponds to these phases. Okay. Specific values of Gibbs potential corresponds to liquid and vapor phase. Okay. G1 and G2 represents the specific values of Gibbs potential corresponds to these phases. Then what we can write? We can write this G, this equals to M1 G1, that is for M1 mass M1 G1, and for M2 mass we can write M2 G2. Okay. Okay, that is if G1 and G2 represents the specific values of Gibbs potential corresponds to liquid and vapor state, then G equals to this, from which we can easily conclude dG, this equals to dm1 G1 plus dm2 G2. Okay, we can write this. Now we all know that G, this equals to U plus PV minus TS. So what will be dG? dG will be du plus PdV plus VdP minus TdS minus S dt. So that can be written as VdP minus S dt. Okay. So dG can be written as VdP minus S dt. So at constant pressure and temperature, what we can write? At constant pressure and temperature, we write dG will be 0. Okay. dG is 0. From this, at constant pressure and temperature, dG will be 0. Now if we substitute the value of dG here, that is G1 dm1 plus G2 dm2 equal to 0. Okay, we substitute these values of G. Now what we get previously? We get dm2 equal to minus dm1. Okay, we get previously dm2 means minus dm1, so g2 dm1 will be 0, so from which we can easily conclude g1 this equals to g2. So this represents the equilibrium condition between liquid and its saturated vapor, that is their Gibbs potential must have same value. Okay, from dg we write this vdp minus sdt. Now at constant pressure and temperature dg is 0, fine. Now if g1 and g2 are the two specific values of Gibbs potential, then we can write g equals to m1 g1 plus m2 g2, and from which we find dg. And previously we took a assumption that we consider a unit mass of mixture, that is m1 plus m2, this is equal to 1. So we use this relation and substitute the value, then we get g1 equal to g2. So this is the equilibrium condition between liquid and its saturated vapor. Okay, this is the equilibrium condition between liquid and vapor, that their Gibbs potential, or you can say specific Gibbs potential, must have the same value. Okay, so this is what about the equilibrium condition. Now let us try to find out the second latent heat equation. I also did it in Maxwell's relation chapter, so again I am going to discuss it. So second latent heat equation. Now from second law of thermodynamics we can easily write ds this equals to dq upon t. Okay, now if we consider unit mass of substance that undergoes the change of state from liquid to vapor, okay, you take unit mass of substance. Okay, unit mass of substance, you take unit mass of substance undergoes the change of state from liquid to vapor. Okay, unit mass of substance undergoes the change of state from liquid to vapor, and if S1 and S2 are the entropies of liquid and vapor state, then we can write ds as S2 minus S1. And if we consider unit mass of substance, then we all know dq equals to ml, you put m1, so this will be L, so substitute L by T. Okay, now differentiate this expression with respect to T. ds dt minus ds1 dt, this we can write 1 upon T dl dt minus L by T square. Okay, now multiply this equation by T, so what we get? T ds2 dt minus T ds1 dt, this is equals to dl dt minus L by T. Okay, now what is this? This represents C2, that is the specific heat at vapor phase, and this is specific heat in liquid phase. Okay, so this equals to dl dt minus L upon T. So what we can write? C2 minus C1 plus L by T, this equals to dl dt. So this represents the second latent heat equation. By assuming that unit mass of substance undergoes the change of state from liquid to vapor, okay, where C1 and C2 are the specific heats in liquid and vapor state respectively. So this represents the second latent heat equation. Okay, dear guys, in today's video I discuss about the second latent heat equation and the equilibrium condition between liquid and vapor. Now in our next class I will going to discuss about triple point. Okay, so dear guys, if you don't subscribe my channel, then kindly subscribe it to get latest videos on physics. Okay, thank you.